Hello, I'm Richard Brown, and thank you for joining me for this presentation, which I've titled Understanding the Vortex Ring State, by way of experiment and simulation to a theory. What I hope to describe is some work that began over 20 years ago, but that is still ongoing and that has new relevance in the light of recent developments in the rotorcraft world. The presentation I'm about to give is based on a talk that I gave to the Bedford branch of the Royal Aeronautical Society on the 9th of March, 2022. We had some rather severe technical problems on the night, so no recording was made. Often you find when presenting to an interested and knowledgeable audience that the interaction between the speaker and the listeners can be very fruitful. And that was certainly the case on the evening. I've received some truly insightful comments and questions in the days since I gave the original talk, and I've taken the opportunity in this recording to incorporate some extra material, as well as to expand some of my illustrations to make my points a little more clearly. Also, the live format restricted the talk to about an hour in length. I expect that this presentation will be a little longer than that. I hope that you'll bear with me as I exploit the recorded format to expand a little on some of my explanations and ideas. Feel free to use the pause, fast forward, and rewind buttons if you need to, but most of all, I hope that you'll find this presentation interesting and informative. Also, please feel free to contact me. I'd be very happy to discuss the material that I've presented here with you, and you can find my details on the very last slide right at the end of this recording. I hope that you can see the slides from where you're sitting. Now, although the story I'm about to tell is very much from my own perspective, there are many other people who contributed along the way and that I need to thank. Firstly, the EPSRC for giving us most of the money that supported our research. Then John Perry, a great friend and mentor who sadly passed away just over 3 years ago. As you will see, John's contribution is writ very large over the work that I'll present here. Simon Newman and Gordon Leishman were academic co-travelers, co-authors, and excellent sparring partners when it came to forming ideas coherently and properly. Gary Arlen was my PhD student and is responsible for many of the careful and detailed numerical simulations that I'll present. Murad Khalifa was Simon's PhD student and produced some of the laboratory-based PIV measurements we'll see later. And then many others who contributed in many ways. Ian Simons, AJ Modha, Matt Orchard, Wayland Chan, Richard Green, amongst others. And I sincerely apologize to all those who I haven't managed to fit onto this slide. And last but not least, I'd like to thank Al Brand and Ron Kaiser from Bell Boeing for being so receptive to the work that we were doing here in the United Kingdom. So let's go back to the year 2000, when this amazing flying machine was about to enter service. It's the Bell Boeing V22 Osprey. As you can see, it was part helicopter, part fixed-wing aircraft. It could tilt its rotors upwards to hover or forwards to fly like an aeroplane. In terms of its performance, it promised the best of both worlds. A helicopter in terms of its operational flexibility and a commuter turboprop in terms of its range, altitude, and speed. Then in April 2000, on one very dark night near the small town of Marana in Arizona, 4 Marine Ospreys were simulating a tactical descent to a landing zone on the desert floor. There are several versions of what then happened. In one version, the pilot of the lead vehicle, realizing that his approach was too high, increased his descent rate beyond what had been trialed previously on the aircraft. In another version of the same story, the pilot realized that he was going to overshoot the landing zone. And this is not a particularly uncommon phenomenon in night flying, especially with night vision goggles. And he arrested the forward motion of the aircraft, unintentionally allowing its descent trajectory to become much steeper than he had intended. In any case, within seconds, the aircraft had flipped over on its back and crashed into the desert, killing all 19 Marines that happened to be on board that particular flight. So within short order, an investigation panel was constituted to try to find out what had happened. This was not the first major accident that the V-22 had suffered, And speculation was rife within the rotorcraft community that this accident would be the final blow to the program. The reason for this pessimistic outlook was that a rumor had begun to circulate that the aircraft was fatally beset by an old problem that had last been encountered in the early days of helicopter flight when most rotorcraft were smaller and lighter. This problem was thought to occur when the rotor of the helicopter would descend into its own wake, in the piloting parlance of the time, causing a catastrophic loss of thrust in a phenomenon which was called the Vortex Ring State. So this lecture is about how a small group of us set out to use mathematics and experiment very powerfully together to develop a much more nuanced understanding of the Vortex Ring State, and how we eventually developed a workable general theory for its onset that contributed in a small way to the eventual success of the V22, and that is now used quite extensively by the modern rotorcraft community to manage the phenomenon and to make it tractable in terms of the design of new aircraft. First of all, a little revision might perhaps benefit those of us who are a little bit rusty in terms of their helicopter aeromechanics. It's also perhaps best to make sure that we understand rotor behavior under normal conditions before we go on to consider rotor behavior under more pathological circumstances. So the basic question we might ask is, how does a rotor generate thrust? And in some ways, this fundamental issue lies at the heart of this presentation. The first resort is usually to consider the rotor as an actuated disc, which then creates a long vertical wake which streams down into the flow below the rotor. And here I'm showing the situation with the rotor in hover. The rotor as an actuated disc accelerates the flow from rest far above it to a value which we will call VH, the hover-induced velocity at the rotor itself. In so accelerating that flow, Newton's second law then applies, and an opposite force must be generated on the rotor, which we call the thrust. Now, the interesting thing about the wake is that it continues to accelerate the flow, so that far below the rotor, the speed of the flow approaches something like twice VH. And this is another crucial point to keep in mind. If this rotor wake is not there, then this additional acceleration of the flow doesn't take place, and the rotor doesn't generate the same amount of thrust for any given value of VH. Now let's get a bit more specific and try to relate the thrust produced by the rotor to the acceleration of the flow. If we apply Newton's laws to the flow, then we can very quickly show that in hover, the result I've shown over here applies. In other words, the square of the hover-induced velocity is proportional to a parameter over here, which we'll call the disk loading. It's effectively the weight of the helicopter divided through by the area of its rotor disks. Now, if you believe this momentum theory, then it gives you an estimate of the hover-induced velocity that a rotor with a given disk loading will produce. Even if you don't believe momentum theory, and shortly we'll begin to see that despite being very useful, it does have its deficiencies, then this result gives us a very useful way of codifying the disk loading in a variable which has the dimensions of velocity, and which we can then treat as a scaling parameter within the rotor system. I'll show you how we do this in a few slides' time. Talking of scaling laws, it's also possible to very quickly show that for helicopters that are all geometrically much the same, the disk loading should scale roughly as the cube root of the weight of the helicopter. Here I've plotted the disk loading of a whole set of conventionally configured helicopters against the log of their weight, and they all fit this trend rather well. All these blue points represent actual helicopters. So at the bottom end here, we have the Bell 206 with low weight and disk loading. And up here we have the CH-53E, which is a heavy helicopter with a high disk loading. The basic principle appearing to be that bigger conventional helicopters tend to have higher disk loading. Now you'll see something quite unusual already. Here's the V22, and here's where it sits on this graph. You can see that it's a heavy machine, but also that it has a disk loading that is rather high by conventional helicopter standards. So perhaps we can already see that there might have been something extraordinary about the V-22 that perhaps hadn't been quite appreciated during its original design when the aircraft's performance had been considered. Another thing worth bringing to our attention right at the beginning, because I'm going to use this representation extensively, is how we go about representing a descending flight trajectory for a helicopter. Now, this representation on the left perhaps seems the most intuitive. We plot altitude on the vertical axis, and we plot distance on the horizontal axis. And the helicopter might, let's say, start in steady level flight for a while over here, before accelerating into descent, perhaps reaching a steady descent rate, and then slowing down to a stop in hover before settling onto the ground. Now, for aerodynamic reasons, that's not a particularly effective way of representing a descending flight trajectory. Essentially, we don't expect the physics of the vortex ring state to be much influenced by where the helicopter is in the sky, but rather by its speed relative to the air through which it is flying. So what we tend to do is to represent a descending flight trajectory using this form on the right instead. To get from the one representation to the other, all we do is differentiate the aircraft's trajectory with respect to time, so that rate of change of distance becomes the forward speed of the helicopter, and rate of change of altitude becomes the rate of descent of the aircraft. Then if I replot the blue trajectory on these new axes as the red curve over here, then you can see that we may start off in steady level flight on the horizontal axis over here. We'll accelerate into descent. We might reach a steady descent condition over here. And then we might decelerate back into hover. And hover, very conveniently, is the origin on this set of axes. So bear in mind this representation, because we will use it extensively in the slides to come. Okay, so where are we going with all this? In the course of this presentation, I'm hoping to do three different things. The first thing I'm going to do is to talk about the vortex ring state as an operational issue, how the pilot actually experiences the phenomenon. Then I'm going to spend quite a bit of time talking about our theoretical understanding of the vortex ring state. I'm going to show how the classical piloting description of the vortex ring state as descending into the Rotawake is deficient to the point of being wrong, and then proceed through a series of logical steps to introduce a more sophisticated view of the onset of the vortex ring state that is more consistent with the physics as we understand it. What I'll then do, using this more nuanced description of the vortex ring state, is to show the practical consequences for the next generation of rotorcraft, many of which have characteristics which are likely to make their behavior in the vortex ring state very similar to that of the V22. So let me try to show you what the vortex ring state actually looks like from the pilot's perspective. Let's try to fly this trajectory, starting in steady level flight, accelerating into descent, trying to maintain a steady descent rate for a while, and then decelerating back into hover. So let me try to show you what the vortex ring state actually looks like from the pilot's perspective. This video shows quite clearly what happens. Don't worry about the water spray that's added here to try to illustrate the behavior of the wake during the descent. That's not in fact showing what the creators of the video would like us to believe it's showing, and is actually a bit of a red herring. What I'd like you to concentrate on is the trajectory of the aircraft as it descends along its flight path. So here we see the helicopter in steady level flight, more or less. And the pilot puts it into a gentle descent and then starts to accelerate. At first, the descent looks rather controlled, but soon matters get away from the pilot and the descent rate starts to look rather alarming. Eventually, the pilot takes a corrective action and arrests the descent using a technique called the V-shot maneuver, which is a very modern way of escaping vortex ring conditions. The important thing to take away from this video is the very sudden increase in the descent rate that accompanies the onset of the vortex ring state. I don't really want to present that sort of material here, but if you go to somewhere like YouTube, you'll find a handful of videos which show the helicopter not being able to escape the VRS before colliding with the ground, often with fatal consequences for the pilot and crew. So just to recap what happened in the video. The pilot was trying to fly this dotted trajectory over here, but what he ended up doing was flying this other trajectory over here, where at some point the descent rate started to increase, got away from the pilot for a while until he managed to regain control and to recover to some condition over here, perhaps with quite high forward speed or descent rate. Okay, so this diagram shows the typical flight trajectory through the vortex ring state, where the pilot suddenly experiences this increase in descent rate that he wasn't anticipating. Now, most of this presentation is going to be about what happens near this point over here. You can imagine that there might be a boundary somewhere here in the flight envelope that marks the onset of the vortex ring state. Now let's go back to the piloting perspective and look at the VRS from another angle. Pilots tend to encounter and manage the vortex ring state in one of two different ways. These two diagrams try to show the differences. On the horizontal axis is the descent rate of the helicopter, increasing from right to left. I've then plotted the variation with descent rate of three different variables that are of interest to us as the aircraft descends into the vortex ring state. The collective pitch setting at the top, the thrust at the bottom, and in the middle, the passage of time as the aircraft flies the descent trajectory. In the left-hand diagram, the pilot holds his controls fixed as the aircraft descends. As you can see, the pilot's collective pitch input remains constant as the descent rate of the aircraft increases. In the right-hand diagram, the pilot tries to keep the acceleration of the aircraft constant, as you can see from the relatively linear variation of elapsed time during the descent. He does this by varying his collective pitch input so that the mean rotor thrust, shown as the blue dashed line, remains roughly constant during the descent. In both scenarios that I've plotted here, the pilot sets himself up in an accelerating descent by reducing the collective pitch so that the thrust generated by the rotor is somewhat less than that required to sustain level flight. If, as on the left, he holds the collective pitch constant, then as the helicopter accelerates into descent, the mean thrust generated by the rotor, again shown by the blue dashed line, remains roughly constant or even increases a little for very low descent rates. However, once a critical rate of descent is reached, the thrust produced by the rotor declines precipitously, and the aircraft descent rate starts to increase rather dramatically, as you can infer from the flattening out of the graph of elapsed time that you can see over here. The rotor exits the vortex ring state with the aircraft descending at a very high speed. Another important characteristic of the vortex ring state is the presence of these fluctuations in the thrust. Relatively mild, while the aircraft is in what we might call incipient vortex ring state conditions, but then building up to become very large and upsetting with the rotor within the fully developed vortex ring state. If, on the other hand, the pilot tries to keep the acceleration of the aircraft constant by manipulating the collective pitch as the aircraft descends, then this graph shows what happens. As the aircraft accelerates into descent, the pilot has to compensate in order to keep the rotor thrust more or less constant by pulling up on the collective in a fairly counterintuitive response to the dynamics of the aircraft in terms of its vertical acceleration. In the same way as in the previous case, the aircraft is also subject to these fluctuations in the thrust produced by the rotor, and these fluctuations are most intense with the rotor having entered a fully developed vortex ring state. Now, one of the problems of identifying the onset of vortex ring state to any level of rigor is to find a variable within the whole panoply of flight measurable quantities that reliably indicates that the rotor has actually entered the vortex ring state. When I show you some of the data from the VRS test program that was conducted for the V22 Osprey later in this presentation, you'll see that a combination of variables is often used in mutually corroborative form to determine the onset of vortex ring state. But from these graphs, you might think that the presence of these thrust fluctuations might be a good indication that the rotor has in fact entered the vortex ring state. And with some reservations, that is indeed the case. So over the years, there's been an intensive effort to try to map out the part of the flight envelope where these thrust fluctuations might actually be encountered. What I've done in this figure is to plot a pretty comprehensive range of the available experimental data showing where in the flight envelope, defined in terms of the forward speed and rate of descent, these VRS-related thrust fluctuations are encountered. The experimental data goes all the way back to the 1940s, and the earliest flight test experiments through to the 1990s and Betzina's experiments on a model V22. Now you'll see that something rather special is going on here. I'm not plotting forward speed and descent rate in conventional units, such as meters per second, knots, or feet per minute. Instead, I'm plotting the data on axes where the forward speed and the descent rate have both been non-dimensionalized by dividing through by the hover-induced velocity VH that I introduced on the second or third slide of this presentation. What becomes very apparent if we adopt this non-dimensional representation of the flight envelope is that all the data for the location of these VRS-related thrust fluctuations, independently of the experimental setup or the rotor that was involved, tends to cluster in the same part of the diagram. Now that's a crucial observation because it enables us to make an important theoretical advance. In fact, this clustering of the data on the non-dimensionalized flight envelope suggests to us that the existence of the vortex ring state is a universal characteristic of all rotors. In other words, we won't find that some rotors are subject to one kind of vortex ring state and others to another kind, or not at all. Now let's try to formalize this. Instead of presenting the VRS domain on this dimensional representation of the flight envelope, the data suggests that we should instead turn our attention to this non-dimensional representation, where we divide the forward speed and the descent rate both by the hover-induced velocity. Now here's where we exploit the equivalence between the hover-induced velocity and the disk loading that momentum theory gives us and that I introduced earlier in the presentation. We can either non-dimensionalize using the hover-induced velocity or the square root of the disk loading. It doesn't matter, the result is the same. What this change of variables embodies, if you like, is this basic theoretical assumption that all rotors are subject to the same sort of vortex ring state, up to a scaling of the size of the region of the flight envelope that is affected by the VRS by the hover-induced velocity, or equivalently by the square root of the disk loading. If you accept the argument so far, then you realize also that the details of the design of the rotor, so parameters such as the blade twist, the blade tip shape, and anything else you might imagine, the number of blades perhaps, must all have only a secondary influence on the character of the vortex ring state that the rotor will be subjected to. So in other words, although we may need to consider the details of the rotor design to understand the subtleties of the VRS that a particular vehicle may encounter, this is secondary to the idea that the major characteristics of the VRS are determined principally by the disk loading of the rotor. Now, how is this used in practice? Well, in terms of its operational relevance, this particular set of experimental data seems to have taken on a life of its own. In 1966, Washizu and Azuma at the University of Tokyo did some experiments on a 1 meter diameter model rotor, and they mapped out comprehensively the region of the flight envelope that was subject to VRS-related thrust fluctuations. This figure shows their results presented in the form of a contour map of the amplitude of the thrust fluctuations that they were able to measure. The data certainly supports the idea that the VRS is confined to a particular region of the flight envelope. Taking their results at face value, you might, for instance, conclude that the vortex ring state will only be encountered if the helicopter is flying through the air at a forward speed that is smaller than the hover-induced velocity and simultaneously is descending at a rate that is somewhere between 0.5 and 1.5 times the hover-induced velocity. You can also see how those definitions may serve to give us our first rough and ready, very crude and empirical definition of the VRS onset boundary. Later on in this presentation, I'll show you that we can do very much better with a little theoretical input. Now, there is a danger in trying to take the arguments that I've presented in the last few minutes a little too far. For instance, Reynolds number effects may play quite a strong role in making the thrust fluctuations experienced by a model rotor a little more benign, for instance, than is the case for a full-scale system. And certainly if you look in detail at the data that I presented a slide ago, you'll see evidence of these second-order effects. But let's have a closer look at how non-dimensionalized data such as this can be used to produce useful information to inform the piloting of any given rotorcraft. Well, the interesting thing is that Washizu and Azuma's data has propagated its way directly through into the flight manuals of many helicopters. So if you're familiar with the flight manual of the CH-53E, you'll see a diagram which looks something like this. And you can see that these contours over here, which are meant to demarcate the region of the flight envelope in which the aircraft might encounter the VRS, have more than a passing resemblance to Washizu and Azuma's curves. The important difference here, though, is that the units on the axes are real rather than non-dimensional. Washizu and Azuma's data has been scaled using the disk loading of the actual helicopter to give a diagram that is specific to the vehicle. Now, if you happen to be a US Navy pilot, then the diagram will come with an additional boundary called the NATOPS boundary. And you'll see this feature again when I present V22 data later on in this presentation. And there'll be strict instructions not to fly below that NATOPS boundary. So at low forward speed, flight is allowed in this low descent rate corridor over here. But as the forward speed increases, the corridor widens and the pilot is able to exploit a broader range of descent speeds. But if we compare the flight manuals of two different helicopters, then what we'll often find that these diagrams just map from one aircraft to the other. So if we compare the flight manual entry for the CH-53 on the left with that of the Bell 206 on the right, then you can see that the two diagrams are practically identical, except for the numbers on their axes. For the CH-53, the top of the VRS domain is encountered at a descent rate of about 2,000 feet per minute, whereas for the Jet Ranger, the equivalent descent rate is about 1,000 feet per minute. And if you remember, the Bell 206 has got a very low disk loading compared to the CH-53. And to give you an illustration of just how much the disk loading does affect the size of the region of the flight envelope that is subject to the VRS, I'll rescale the right-hand diagram so that its axes are the same as for the left-hand diagram. And then I'll overlay the two sets of information. And what you see is that the VRS envelope for the Jet Ranger with its low disk loading is relatively tiny compared to that for the larger, heavier helicopter. Hence the persistent idea amongst some elements of the rotor community that the Vortex Ring State is not a particular problem for smaller aircraft. The data that I'll present later in this presentation should dispel any complacency in this respect, however. It's the disk loading that matters, not the size or the weight of the vehicle. I'll return to this idea of universality of the Vortex Ring State later on in this presentation. But for the moment, let's change direction a little. So up to now, I've been talking quite extensively about the Vortex Ring State from an operational perspective. I've tried to give you a qualitative understanding of what the VRS looks like from the piloting point of view, and I've also shown you how the possibility of encountering the VRS might be represented within the flight manual of a particular helicopter. I've also begun to expose some quantitative aspects of the phenomenon, for instance, in terms of its dependence on the disk loading and its existence over a bounded range of flight speeds and descent rates. But the arguments so far have been largely heuristic and based on an analysis of experimental data. So in the next section of this presentation, I'd like to develop our theoretical understanding of the fluid mechanics that underlies the Vortex Ring State. Now, let's say that we want to try to predict the thrust that is produced by the rotor when operating within the Vortex Ring State. Let's try to do that by going back to our original approach, where we related the acceleration of the flow through the rotor to the force that it produced. We can quite easily extend the analysis to the situation where the flow away from the rotor is not at rest, obtain a result for the induced velocity of the rotor, then use this to calculate the thrust. This graph shows how the induced velocity created at the rotor varies with the climb rate of the helicopter when in vertical flight, as predicted by this momentum theory. When the helicopter is climbing, the theory provides a very sensible and useful estimate of the induced velocity through the rotor. Similarly, for very high descent rates, particularly those at greater than twice the hover-induced velocity. Unfortunately, in precisely the region of the flight envelope that we are interested in other words, for descent rates between 0.5 and 1.5 times the hover-induced velocity, momentum theory starts to give us problems. We can only get some form of result, shown in the red dashed lines here, if we're prepared to sweep some divisions by zero under the carpet. In other words, momentum theory fails to produce useful results precisely within the VRS regime. Now, perhaps we can do one of two things. We can either claim that the theory is useless, throw up our hands and go back to the textbooks to find another, hopefully more appropriate formula, or we can try to find out what the theory is trying to tell us. Simple theories are often like that. They tell you more about the physical world when they break down than when they're working properly. So what we find, if we look a little bit more deeply into the theory, is that the problem within this region of the diagram is that the velocity somewhere along the stream tube containing the flow through the rotor is going to zero. The diameter of the stream tube then goes to infinity, and the whole analysis breaks down. Now, the question that we might ask ourselves is, could it be that our conception of the shape of the wake that is created by the rotor is in fact faulty? So let's go back to experiment. Some very careful data gathering shows us that the mean thrust that the rotor generates when operating within the vortex ring state does seem to follow a consistent and repeatable relationship to the descent rate of the helicopter. Given what I've said so far about thrust fluctuations and the associated unsteadiness of the loads on the aircraft within the vortex ring state, this order within the chaos may come as a bit of a surprise. What this suggests, of course, is that we should be able to find a deterministic, well-behaved relationship between the induced velocity and the descent rate of the helicopter that applies within the vortex ring state. Now, this solid black line shows what happens if you forego one of the major underpinning assumptions of momentum theory. And instead of assuming that the wake extends effectively to infinity below the rotor, we assume instead that the wake is finite in extent, as I've tried to illustrate in this small diagram to the right. By modeling the length of the wake as a function of the descent rate of the rotor, you get a very sensible agreement, in fact, between the theory and the experimental data. Now, this sort of result is again crucial because it shows us where we should perhaps focus our attention in trying to understand the physics of the vortex ring state. And up to this point, of course, I've not really said very much about the rotor wake, except perhaps for a few rather indirect references. It's time to rectify that. Each of the pictures on this slide tries to represent the structure of the wake that is produced by the rotors of the helicopter. Essentially, the rotor is constructed from a set of blades. In rotating about the hub of the rotor, each of the blades generates lift in much the same way as an aeroplane wing does. And in much the same way as an aeroplane wing does, each blade also generates a pair of trailing vortices, one at the root of the blade and one at the tip. The loads on a typical helicopter rotor blade tend to be concentrated near the tip, giving a particularly powerful tip vortex, however, compared to the root vortex. Now, as the helicopter moves through the air, and because of the flow that is induced through the rotor by these vortices themselves, these tip vortices convect away from the rotor to form these essentially helical or spiral patterns in the air. With the rotor near hover, the spiral structure of the vortices in the wake is the clearest. Here's a V22 flying pretty close to hover, and you can see the helical structure of the vortices in the wake because of the condensation in the cores of the individual blade tip vortices. With the helicopter in forward flight, the mutual interference of these vortices can lead to a very complex but still inherently spiral wake structure. I'll say a lot more about this mutual interference between the vortices later. Now, in terms of the influence of these vortices on the rotor, it's useful to think of them as the location of extremely intense and localized swirling motions within the airflow. So if the vortices get close to the rotor, their influence on the aerodynamics and the loads produced on the rotor blades becomes more pronounced. So again, let's go back to experiment and see what it can tell us about the structure of the wake of the rotor in descending flight. Down the middle of this diagram, we have a rather simplistic representation of what the gross characteristics of the flow might look like as we move from hover at the top, where the flow is essentially downwards through the rotor, through to rapidly descending flight at the bottom, where the flow has changed direction and is predominantly upwards through the system. At the left, we have some shadow graph images which show the location of the individual vortices in the wake, taken as a snapshot in time. In hover, you can clearly see the individual helical vortices from the rotor blades streaming down into the flow. Similarly, in rapid descent, these vortices are still there, although you can see that they now stream upwards, as you might expect, into the flow above the rotor. In the middle here, though, with the rotor in descent at some intermediate speed, you can see that the individual vortices are still present, but they are clustered around the rotor, and instead of having a nice helical structure, they look quite battered, bent, and deformed. These particle image velocimetry images at the right give us some further insight. Remember that PIV involves averaging of snapshots of the flow over time, so that only coherent, persistent, or repeatable flow features will be represented in the data. So we see this coherence in the images for hover and for high-speed descent. But if we look at the images for the wake of the rotor when the descent rate is just right to create vortex ring conditions, then there's not enough coherence in the vortical structure of the wake for anything to register in the image. So what's going on? What causes this effective disappearance of the rotor wake in VRS conditions? Now, if you go to your average helicopter flight school, you'll very likely be given quite a simple explanation for why the VRS comes about. The usual way of describing things is that VRS occurs because the helicopter rotor descends into its own wake. In the next few slides, I'll try to put this explanation on a theoretical footing, but then I'll also show that in the light of available data, this idea is too simple, perhaps simplistic even. Okay, so how does this simple explanation work in terms of the wake dynamics? Let's adopt yet another way of looking at the dynamics of the vehicle, this time together with the dynamics of the individual vortices within the rotor wake. I've plotted time on the horizontal axis, and on the vertical axis, I've plotted the vertical position of the rotorcraft with respect to some datum. Using these axes, I can represent the helicopter as it descends through the air as this sloped green line. So as time marches on from left to right, the helicopter descends through the air. I can represent the vortices similarly. Each of these black lines represents one of the blade tip vortices. If these vortices travel fast enough, then they can escape the rotor and descend into the flow to form a wake below the system, as I've shown in this little diagram over here. So with the situation as drawn here, a coherent wake is able to form and the helicopter is not subject to VRS. Let's increase the descent rate though and see what happens. You can quite easily see that there's a critical condition where the helicopter catches up with its own vortices as they convect down into the flow. In that case, the helicopter rotor collects up all the individual vortices, and you might imagine then that these bundle up around the rotor to form a big, fat, powerful ring-like vortex. So here we have the standard explanation of the origin of the vortex ring state. The helicopter descends into its own wake, and the effect of this vortex bundle is to destroy the ability of the rotor to generate appreciable thrust. Highly compelling, but unsubtle and not really supported by detailed analysis, as I'll shortly show. So what happens if we increase the descent rate of the vehicle further, as I've shown in this diagram? Well, then the rotor can leave these vortices behind in the flow again, and the helicopter can escape its own wake, so to speak, and the rotor's encounter with the vortex ring state comes to an end. Now, the interesting thing is that you can actually develop an analytical model for the location of the VRS onset boundary on the flight envelope based on this conception of the dynamics of the rotor wake. That was done by Volkovich in 1972. The diagram at right shows the location of his onset boundary on axes of non-dimensionalized forward speed and descent rate. According to his model, the rotor would enter the VRS if it crossed this lobe-shaped boundary in the flight envelope. Now, if we compare Volkovich's model's predictions against the experimental data, and here again, I've used Ushizu and Azuma's measurements of the thrust fluctuations that are experienced by the rotor when in the VRS, then we can see that there's potentially a serious problem. Volkovich's model predicts VRS onset occur at a descent rate that is about equal to the hover-induced velocity, whereas the data suggests that VRS onset occurs at much lower descent rates, around about 0.5 times the hover-induced velocity. Volkovich also had significant problems explaining why the VRS didn't persist when the forward speed of the helicopter was increased beyond VH, and had to resort to a very obscure explanation in terms of the profile drag on the rotor. So this is where John Perry made a really big insight. What he postulated is that the induced velocity created by the rotor in its wake is actually not as effective as we think, given this very simple convection model. And what he was able to do was to come up with a very simple analytical expression, which I've written down over here to define the location of the VRS boundary within the flight envelope of the helicopter. Mu-x is the non-dimensional forward speed of the helicopter, and mu-z is its non-dimensional descent rate. Those of you who remember some of your high school mathematics might recognize the form of this expression as being very similar to that of an ellipse. R squared is equal to ax squared plus by squared, in other words. And indeed, John's expression defines a distorted, elliptical-shaped lobe within the flight envelope that marks the onset boundary for the VRS. This elliptical shape has just two parameters, but captures very well the region of the flight envelope in which Washizu and Azuma's data suggest that the rotor might encounter the VRS. The first parameter, mu-w, John postulated, was a critical rate of transport at which the wake would collapse out of its coherent state to yield the vortex ring state. And the parameter k was introduced in the realization that the mechanisms governing transport of the wake down away from the rotor might yield a different wake transport velocity than those mechanisms that govern transport parallel to the rotor disk. The match between John's model and Washizu and Azuma's data was much better than obtained with the older Volkovich model. The descent rate for VRS onset is predicted correctly at about 0.5 times the hover-induced velocity, and the part of the flight envelope affected by the VRS extends out to speeds that are about equal to VH in both cases. It may look as though the bottom of the VRS, as predicted by the model, might extend to too great a descent rate, but here's where the limitations of Washizu and Azuma's small-scale model-based experiments are likely playing a role. Data that I'll show you a little later, obtained on much larger systems, tends to fill in the gap here. The problem with this particular model, though, is that we have these two parameters, mu-w and k, and they're essentially empirical at this stage. The best values for these parameters are obtained by curve fitting to the available data. That's not ideal, and we'd make a major advance if we could understand where these parameters actually came from. It would be ideal, for instance, if we could predict the values of those two parameters given a more fundamental understanding of the physical processes at work. Remember, too, that John's model is based on this idea that the vortices in the rotor wake, or at least their influence on the conditions at the rotor, do not propagate as quickly away from the system as the simple convection model would suggest. This is largely just postulation at this stage, and to put the model on a firm physical basis, we should really seek a better understanding of the physical processes at work. So how would we go about doing that? Well, one way is to investigate the wake dynamics in more detail using computational simulations of the underlying fluid mechanics. Now, modeling the dynamics of individual vortices in the wake of a helicopter rotor is an extremely exacting task. Now, you might think that the standard recourse would be to some sort of computational fluid mechanics. But the problem with most CFD methodologies is that they tend to dissipate and lose sight of the very vortical structures that are of most interest in understanding the VRS. At the time, my research group was developing a new computational approach to rotor wake modeling called the vorticity transport model, which was designed from the outset to avoid these problems. As it turned out, the VTM was able to represent the dynamics of the wake very accurately and efficiently, especially in these taxing problems where many rotor revolutions were required to capture the inherent properties of the VRS. This video shows the approach being used to model the aerodynamics of a modern tilt-rotor vehicle in forward flight. And you can see for yourself how the specialized methodology is able to capture the dynamics of the helical vortices all the way from their inception at the rotor blade tips and maintaining their integrity and coherence way back to many rotor revolutions behind the aircraft. So what we could do with the VTM is to fly a model of the helicopter rotor in a vertical descent. In these initial exploratory runs, the trajectory followed by the helicopter was not very important. We could do something very simple, like starting from a very high descent rate and forward speed outside of the vortex ring regime, and then slowly decelerating the aircraft and reducing its descent rate until we ended up deep within the vortex ring state. So let's see what happens if we simulate this trajectory using the vorticity transport model. Okay, so what we're trying to do here is to take an initial peek into the dynamics of the rotor wake as the helicopter decelerates from a high-speed descent into the vortex ring state. So first we start the simulation and allow sufficient time for the wake to build up with the helicopter in rapid descent. I'm plotting the wake vorticity on a cut through the plane of lateral symmetry of the aircraft, and you can see the individual tip vortices from the main rotor, as well as the vorticity from the fuselage wake, as well as that generated by the tail rotor. The first important observation is at this very high descent rate, the structure of the main rotor wake is very coherent indeed. All the individual tip vortices are visible, and the spacing between them is very even. But watch what happens now as the rate of descent of the aircraft slowly decreases. Look over here. Something very interesting is about to happen. The wake is losing its coherence, starting from far downstream of the rotor and moving incrementally downwards towards the rotor as the descent rate decreases. And you can see that it's not that the individual wake vortices are bundling up as per the classical explanation. They're actually being disrupted and turned into highly disordered vortical mush. The vortices are being changed entirely in character by this physics going on in the wake. All the vorticity is still there. Look, you can see it all streaming up the middle of the wake there, but it has a very different character to the tip vortices that the rotor originally created. And once we're down in deep vortex ring conditions, there's no real sign of the coherent bundled set of vortices that we might have imagined from the classical description of the vortex ring state. The whole vortex system has been torn up, disordered, and ejected out of the center of the rotor disc. Let me just reinforce that by showing you this set of images of the rotor wake at various points along this decelerating descent. At the highest descent rate, you can see that we have a coherent wake. But at the lowest descent rate, with the aircraft deep in the vortex ring state, you can see that the vortex wake has completely lost its coherence. You can see that best over here, where it's clear that the individual tip vortices have been transformed into this turbulent mush of tangled vorticity fragments. So much for the idea of the helicopter descending into its own wake. It's not really that at all. It's in fact that the vortex wake is changing its character completely. So what's going on? Simulations such as this show very clearly that the physics that governs the onset of the vortex ring state is a lot more complex than we might have imagined. Really, what's implicated in these sorts of results are the effects of wake instability. Now, rotor wake instability is not entirely unknown within the rotorcraft field. These pictures show a range of situations where the effect of vortical instabilities are acting to disrupt the orderly structure of the rotor wake. The common feature in all these cases, though, is that the disruption only becomes apparent relatively far downstream of the rotor itself. So in forward flight, the individual tip vortices eventually roll up to form these larger supervortex structures some distance behind the rotor. Similarly, in hover, the interaction between the tip vortices eventually causes the wake to evolve these larger, less ordered structures in the flow some distance below the rotor. The first thing to realize is that vortical instability in the rotor wake provides an explanation for an effect that we've already encountered much earlier in this presentation. If you remember, in an earlier slide, I presented this diagram showing how we could generate an analytical model for the induced velocity that was created at the rotor. Unlike with momentum theory, which failed to give sensible results within the VRS, the new analytical model applied all the way from ascent through the VRS and into rapid descent. If you remember, to create this model, we had to assume that the wake, instead of being infinite in extent, actually had a finite length. This observation that the instability in the rotor wake is capable of disordering the individual tip vortices and turning them into a decoherent, diffuse cloud of vorticity fragments some distance below the rotor lends support to the idea that the wake does in fact behave as though it has finite length. As I've tried to show in this schematic, comparing the wake structure that is assumed by momentum theory to this conception in terms of wake instability, the effectiveness of the lower portions of the wake is essentially being negated by the vortical instabilities. Now let's try to dig a little deeper into the physics of wake instability. and then apply our understanding to the dynamics of the wake as the rotor enters the vortex ring state. Let's first make a few simplifying assumptions so that the problem becomes tractable to the point that we can do some analysis. Now, we know that the wake consists of vortex structures that are helical in shape, but let's first approximate the topology of the wake and instead represent the sequence of vortex filaments as a series of ring-like vortex loops. Then let's analyze the behavior of one of these vortex loops on its own. It turns out that there are two important modes of instability that we need to consider. The first mode is called the short wavelength instability. If we take this vortex loop and perturb it slightly by adding a few wrinkles, then the vortex responds by deforming and crinkling, as shown in this animation. If we represent the wake by a sequence of vortex loops and then perturb one of the loops, then something very interesting happens. The deformation of the loop that I originally perturbed continues to grow as a result of a process called self-induction. But because of the mutual interaction between the loops, the instability also spreads out along the loops as time advances. And you can see that the spreading takes place in both directions from the location of the original perturbation. This observation is crucial for a more nuanced view of vortex ring onset. To put it in other words, the products of the instability of the Rotawake filaments travel out at a different speed to the speed of the vortex filaments themselves. You can see also from the simple representation that the shortwave instability is capable of creating extensive disorder within the wake. And indeed, some further theoretical work shows that this disorder can be created within very short timescales, indeed over the course of a few rotor revolutions for the biggest disturbances. Now we need to ask ourselves another question. How are the initial perturbations created that then allow the short wavelength mode to create such disorder in the wake? Well, that's the work of another instability resulting from the pairwise interaction between neighboring vortex loops. If we look at the dynamics of two isolated vortex loops, then they propagate through the flow by effectively swapping position, as shown in this animation. The mutual interference causes the leading vortex to expand and the trailing vortex to shrink. The leading vortex then pulls the trailing vortex through to the front in this leapfrogging type motion. Now, if we consider the leapfrogging mode applied to the vortex wake, then we can't neglect the helical nature of the vortex filaments. The fact that the loops of the wake are interconnected to form a helix poses what's called a topological constraint on the dynamics of the system. The helical form of the filaments prevents the loops from exchanging position and instead causes any leapfrogging motion just to tangle the vortex filament, as shown in this animation. Now, if you think this is all a bit theoretical, there's some really fantastic water channel visualization that's been done of the evolution of a helical vortex. Have a look at this. It's quite beautiful in terms of the quality of the experimental data, and you can see this leapfrogging mode in action, as well as its effect in tangling up the vortex filaments. So in summary, the leapfrogging mode is capable of causing very large local perturbations to the structure of the wake. And then the short wavelength mode can take over to complete the destruction of any coherence and order in the vortex filaments that might remain. Now let's do a simple numerical calculation that shows the combined effects of leapfrogging and the short wavelength instability. Unlike with the previous calculations I've shown you, this calculation is for a system that has been pared back to reveal just the essential physics. Often I think that numerical practitioners forget the value in being able to do this sort of thing. One doesn't have to represent the physical world in all its detail to learn something about the system. And indeed, this approach often obscures true understanding. So here we instead model the wake dynamics of a simplified rotor, which only generates one single helical tip vortex filament. You can see that for the first few revolutions below the rotor, the tip vortex remains relatively coherent and maintains its helical shape. As I step through the simulation, though, you'll see a series of leapfrogging events taking place just a little further down in the wake. So there. And there again. And you can see that the effect of these leapfrogging events is to tangle and distort the tip vortex, effectively destroying its helical character. The short wavelength mode then takes over to produce this cloud of scattered, disordered, and dismembered vortex fragments at the bottom of the diagram. Now we can use our understanding of the dynamics of the wake in the presence of these instabilities to produce a rather more sophisticated and nuanced model for the onset of the vortex ring state than the classical convection-based approach gives us. Okay, so let's just refresh our minds as to how the classical model works. As before, I'm simultaneously representing the motion of the rotor and one of its vortices on a diagram where the horizontal axis represents time and the vertical axis represents vertical position. In the situation shown, the vortex descends into the wake faster than the rotor, so it is able to escape into the flow below the system. In the classical case, we'd conclude that the rotor was descending too slowly for it to be subject to the vortex ring state. Let's then enhance this model by adding in the effects of vortex instability. We know that the disturbances to the wake that result from its instability grow in strength as time progresses, but then dissipate as the vortex filaments disintegrate and disperse some distance below the rotor. We also know, though, from our previous analysis, that the disturbances are capable of spreading out from their point of origin as time progresses, and we represent this crucial observation by representing the envelope of the wake vorticity plus its disturbances as this wedge-shaped object. As time advances, the region of space that is influenced by the disturbances spreads out on either side of the point of origin of the disturbance as it travels down into the flow below the rotor. Now we change emphasis compared to the original classical convection model. We identify the critical condition for VRS onset to take place at the descent rate at which the rotor first catches up with the disturbances within the wake, not with the vortices in the wake as per the classical model. What this allows us to do is to create a very powerful model for the location of the region of the flight envelope that is affected by the VRS, that applies not only under steady flight conditions, but also is able to predict the effects of acceleration and maneuvers on the onset of the vortex ring state. Here I've written this new model in algebraic form after assuming that the aircraft is flying forward and descending at a constant rate. Mu(x) and mu(z) are the non-dimensionalized forward speed and descent rate of the system, and ud and wd are the horizontal and vertical rates of propagation of the vortical disturbances into the wake. Finally, cd is the rate of growth of the disturbances. You can perhaps again recognize the equation of an ellipse in this general form. And indeed, the model predicts the vortex ring onset boundary to be an elliptically shaped curve on the flight envelope, distorted perhaps if ud and w depend, as they usually do, on the flight speed of the aircraft. To make the model practically useful, of course, we need to model the dependence of ud, w, and cd on the dynamics of the vehicle. We can do something else really instructive, however, and compare this new model to John Perry's original model, which I've repeated from an earlier slide here. The two models become identical if we identify the horizontal rate of propagation of the disturbances in the wake as a factor 1 minus k times the forward speed of the helicopter, and the vertical rate of propagation as the same wake convection rate as is assumed in the classical model. So John's postulations regarding the effectiveness of the wake in transporting vorticity away from the rotor and into the flow can be seen here simply as a set of specific assumptions as to how the vortical disturbances propagate along helical vortex filaments within the wake. Equally as interesting is what happens when we identify the rate of growth of the disturbances within the wake in terms of the postulations contained within John's model. We see that John's model is simply assuming that the disturbance growth rate is proportional to the thrust coefficient of the rotor. The coefficient of proportionality is what John thought was a critical wake transport velocity. But because the thrust coefficient is proportional to the disk loading of the rotor, what we see here is the assumption laid bare that the size of the region of the flight envelope that is subject to vortex ring conditions through this radius term in the revised model scales with the disk loading of the rotor. Thus we see the power of John's original leap of intuition when we compare his model against this new, more rigorous analysis. Finally, we close the loop by showing that his two rather hand-wavy parameters, K and mu W, can be understood in terms of the dynamics of the wake in the presence of the natural instability of its constituent vortex filaments. Conversely, we can see from this analysis that the better we understand the physics of vortical instability, the better we'll be able to characterize the location of the onset boundary for the vortex ring state in future. So in summary, what we can show is that with certain assumptions regarding the disturbance propagation rates, we can recover John's model as a special case of the more general model. And this certainly leads a distinct amount of credibility to its applicability. In fact, this diagram really puts the cherry on the cake, if you like. What it does is it maps out the vortex ring onset boundary as predicted by this new model onto the experimental data that I showed you earlier. And you can see that there's a surprisingly good match for the boundary of the VRS and the region of the flight envelope, which is subject to those thrust fluctuations that we were talking about earlier. And where I remarked earlier that the model seemed as though it exaggerated the extent of the VRS regime at the highest descent rates, you can see that in the presence of some more modern experimental data, the model actually captures that part of the VRS regime rather better than we might have expected up to now. So here we have a simple model for the onset of the vortex ring state that is well founded in the physics of the Rotawake. Now there's one final mystery to explain, and that is of course to answer the question as to why the V22 that crashed at Marana rolled over inverted during the last seconds of its flight. Well, it turns out that there's likely a problem with aircraft that have widely separated rotors when it comes to the vortex ring state. The velocity at the rotor is what is important for the onset of the vortex ring, and not the velocity of the aircraft itself. So if the aircraft has appreciable roll rate, for instance, then the velocity at rotors located near the wingtips may be appreciably different from one side of the aircraft to the other, and of course possibly very different to the velocity measured by the flight measurement system of the aircraft itself. So let's take another look at our flight envelope, expressed in terms of forward speed and climb rate, and with the vortex ring regime located over here. Then you can see perhaps that there might be various ways of encountering or circumventing the VRS depending on which flight path that we choose. We might follow a safe trajectory, the one marked over here, where we descend at low enough rate once we're above the VRS lobe that we can actually reach hover safely. Or we might overcook the descent rate and actually fly through the vortex ring state itself. But there's this interesting third alternative in the middle, where perhaps because of the roll rate on the aircraft, the port rotor doesn't encounter the vortex ring state, but the starboard rotor does. In which case, if the aircraft's control system is not properly set up to cope with this sort of dissymmetry, one might end up exacerbating the vortex ring state to the extent that the thrust falls away on the starboard rotor in this particular example, and the aircraft ends up encountering a very high roll moment, which could turn the aircraft upside down and lead to the kind of accident that happened at Marana in 2000. In the final part of this presentation, I'd like to look at some of the practical applications of this model for the onset of the vortex ring state. I'd like to concentrate specifically on its implications for the next generation of rotorcraft that are just leaving the drawing boards, or these days, should I say, the CAD systems at various companies, as we see what can only be described as a boom in interest in vertical takeoff and landing systems for various real-world applications. First of all, let's just recap some of the salient analysis. I spent quite some time earlier in explaining the importance of disk loading on the size of the region of the descending flight envelope in which the rotorcraft would potentially be subject to vortex ring conditions. If you remember, the disk loading is the weight of the aircraft divided by its rotor area. Earlier, I showed the relative size of the VRS regime for two helicopters with very different size and weight by scaling the entries in their flight manuals. Using our model, we can now do that analytically. So here I compare the size of the affected regions of the flight envelope of the Robinson R-22, a lightweight training helicopter, with that of the heavyweight V-22 military tilt-rotor. In generating this figure, I've simply plugged the relevant disk loading into the analytic model to generate the boundary of the VRS onset regime. From this diagram, you can understand where the popular belief might have come from that for small rotorcraft, the VRS is confined to such a small region of the flight envelope as not to be a very important consideration for the safety of the vehicle. Many pilots would disagree with this view, I believe. Indeed, the accident statistics, when properly analyzed, seem to suggest that the dangers posed to rotorcraft flight by the Vortex Ring State continue to be underestimated. In a few minutes' time, I'll elaborate on that perspective. Now, with the aim simply of generating some reference data, let's just sketch out the VRS onset boundaries for a range of rotorcraft that are already in service. So here are some numbers for aircraft that you might recognize. For light utility helicopters, such as the Jet Ranger, the Vortex Ring State is encountered for descent rates between about 500 and 1,500 feet per minute, and out to forward speeds of about 20 knots. Whereas for large heavy transport helicopters, we're talking descent rates of between 1,500 and 6,000 feet per minute, and forward speeds of 30 knots or so. The V22, which we know is an outlier, experiences the VRS for descent rates between about 2,000 and 8,000 feet per minute, and only when the aircraft is flying at forward speeds that are less than about 45 knots. Now, here's the really interesting thing. The world of rotorcraft as we know it is changing rapidly and dramatically. I really enjoyed this picture when I first saw it, a view of the future that perhaps is all too heavily fixated in the present. But it is indeed possible that 2022 may, after many false starts, finally become the year of the flying car. Certainly, if we review developments in the field, there's been a proliferation of new ideas and technologies within the rotorcraft field. Dozens, perhaps even hundreds of companies are competing to produce UAVs, drones, UAMs, and eVTOLs to support various enterprises that aim to change the way that we transport goods and people from one place to another. This slide shows the front cover from the IEEE Spectrum magazine a few months ago and reveals some of the range of eVTOL aircraft that are currently under development. Now, how are these new aircraft likely to be influenced by the Vortex Ring State? Well, in an earlier slide, I suggested that the disk loading obeys a very simple scaling law. It increases as the cube root of the weight of the aircraft. Here I've plotted that scaling law and compared it against actual data for real helicopters, including some of the index cases such as the Bell 206B and Sikorsky CH-53E that I've referred to several times elsewhere in this presentation. All these conventional helicopters obey the scaling law rather well. The V22 has an unusually high disk loading compared to a conventional helicopter, and we've discussed at length the consequences of that. So what happens if we try to plot some of the new generation of eVTOL aircraft on the same axes? Well, try this I did. The first thing you find is that the operating weights for many of these aircraft are secrets that are very closely guarded, presumably for commercial reasons, but that didn't make my life very easy. Of all the candidate aircraft for this comparison, there were only 3 instances where I felt that the weight and disk area measurements that I had were reliable enough to present. And if you plot that data, you find something very interesting. The plot reveals that this new class of aircraft are very different animals to the helicopters that we believe we understand. They are generally very small and light, but compared to helicopters, they tend to have very high disk loading. Now, there may be very good reasons for this. For example, to balance the efficiency of the rotors when operating in forward flight with their lifting ability in hover. But let's stop to consider for a moment the likely impact of the shift towards higher disk loading on the likely behavior of these vehicles when in descending flight. And this diagram, I think, makes the point. I've used our analytical model to generate the VRS curves for the 3 eVTOLs on the previous slide, and overlaying the data on the curves for the various historical rotorcraft designs that I presented earlier. And we can see practically that the high disk loading of these new vehicles expands the region of the flight envelope subject to VRS quite substantially compared to helicopters within the same weight class. in 2 cases sufficiently far to give the aircraft VRS properties that will be equivalent to those of a heavy military transport helicopter or even the V-22. Now, this certainly needs to be borne in mind during the design of the conversion corridor for these aircraft, especially in terms of the trajectories that the aircraft might be designed to follow during the descent to landing. We also need to remember that upwards gusts and tailwinds, which will be common in the operational environment of these new craft, can rapidly and suddenly shift the position of the rotors on this flight envelope, no matter how well designed the nominal trajectory. Finally, many of these new vehicles exploit the distributed propulsion concept to some extent, often having multiple side-by-side rotors. The effects of roll, pitch, and yaw rates in inducing asymmetric VRS, perhaps exacerbated by the mutual interaction between the wakes of the various rotors, needs to be borne in mind also when designing the vehicle to be safe and robust to environmental effects. So the lessons of the V-22 program may be valuable to the designers of these new aircraft in several different ways. After all, the story had a happy ending. The aircraft was cleared for service and entered the US Marine inventory, where it still performs sterling, if not entirely untroubled service. The full story of the huge amount of very hard and diligent work that went into understanding the specific VRS characteristics of the V-22 would take me another hour to explain in appropriate detail. And in any case, the story is told exceptionally well in this paper by Al Brand and Ron Kaiser, which I fully recommend that you read for its practical wisdom. Suffice it to say that an extensive test flight program was conducted to map out the flight dynamic characteristics of the vehicle in descending flight. Most of the effort was concentrated above the NATOPS boundary to make sure that that part of the flight envelope was free of surprises. But several flights penetrated down through the VRS onset boundary proper. The figure at left here shows a typical flight trajectory as flown, showing how a test would typically begin at low descent rate and forward speed, then the descent rate would be allowed to build up until the Vortex Ring State was encountered. Once things got a little too scary, even for the US Marine test pilot, the aircraft would escape VRS by tilting its propellers forward by a small amount, and then recover to steady level flight. The figure at right shows the roller coaster-like nature of the trajectory. Sometimes I consider myself very lucky to be a theoretical aerodynamicist with his feet more or less firmly on the ground. I'll not have the time to discuss the experimental record in detail, but some salient points are definitely worth highlighting. Firstly, the record of the airspeed for the aircraft. Obviously, accurate measurement of the aircraft's speed through the air is vital if the pilot is to have an accurate conception of where his aircraft is on the flight envelope relative to the VRS onset boundary. This diagram at top left shows the difficulty that most practical helicopter air data systems have in providing accurate airspeed data at the low speeds associated with the onset of the VRS, particularly when measurement is exacerbated by the very complex nature of the flow field in which the rotorcraft finds itself under these conditions. Secondly, in the bottom right figure, we see the thrust fluctuations associated with the passage of the rotors through the VRS, with some evidence in this case of dissymmetry in the behavior of the port and starboard rotors. Finally, in the diagrams at bottom left and top right, we see the control inputs that were required to maintain the aircraft on its descending trajectory, and the increased activity of both the pilot and the automatic flight control system with the aircraft at relatively high descent rate is clearly apparent. As I mentioned earlier, it can be difficult to find an objective measure that one can use practically to infer whether the aircraft is subject to vortex ring state or not. Throughout this presentation, I've generally used the presence of the thrust fluctuations, a la Wushizu and Azuma, as such a measure. In this set of tests, the engineers at Bell Boeing experimented with a range of measures, such as the level of activity registered by the automatic flight control system or the roll acceleration error as indicators of the onset of the VRS. These two graphs show those two variables overlaid as contour maps on the flight envelope. And the proof of the pudding in our case was the comparison with our analytic model for the VRS onset boundary, which I'm very pleased to say measured up very well to the flight test data. And that seems to me to be a very good place to end the story. So let me summarize a few brief conclusions. What I've shown effectively is that the prime factor influencing the size of the region of the descending flight envelope that is subject to vortex ring conditions is the disk loading of the rotors. Thinking until quite recently was that this implied that the VRS would only be a problem for large, heavy rotorcraft, and that small, lightweight helicopters would be relatively exempt. The V-22, in a sense, was a warning that it was possible to escape this paradigm by moving away from the conventional idea, if you like, of what a conventional helicopter should look like from a design point of view. And the new generation of aircraft, especially eVTOL aircraft, are very definitely different, being small but having proportionately very high disk loading. This is likely to be problematic if not properly accounted for in the design of these vehicles. We also know that certain design features exacerbate the VRS by changing the rate at which the instabilities within the Rotawake grow and propagate. And I've argued that these instabilities are essentially responsible for the onset of the vortex ring state. So high blade twist, which is good for propeller performance in forward flight, and certain tip shapes, which may be good for acoustics, need to be treated with some care as far as their properties in vortex ring state are concerned. And in particular, the presence of multiple closely spaced lifting rotors, and even more so where there's the possibility for mutual interaction of their wakes, may add an extra dimension of complexity to the behavior of the aircraft when in descending flight. So how might we ameliorate the effects of VRS in our new design? Well, we could perhaps tailor our flight path to keeping above and to the right of the VRS onset boundary. This is a good first step, but it does require detailed knowledge of where the VRS boundary is on the flight envelope. It also requires sufficient margin to account for the effects of atmospheric disturbances and the instrumentation to determine accurately the aircraft's flight speeds and descent rate at low airspeed. For this reason, relying on pilot situational awareness to avoid the vortex ring state is perhaps a little fraught. Ideally, we need to design the aircraft to be inherently safe. And how do we do that? Well, in my opinion, we do this best by improving our understanding of the operational and design factors that have the greatest bearing on the physics of the phenomenon. And in that vein, we've only begun to scratch the surface. So thank you for listening, and I hope that you found what I've said interesting. I've really just given you a taster of this fascinating topic and concentrated very much on how the VRS comes about. I've said a little perhaps about the physics of the rotor once in the vortex ring state, but almost nothing regarding some of the tremendous ongoing work on how to escape the VRS once the wake of the rotor has collapsed. But those are both stories perhaps for another time. As always, please feel free to contact me. My details are here on this slide, and I'd be very happy to discuss this fascinating topic further with you. But for now, this is Richard Brown, signing off until next time.